This is the lecture on Chapter 3, Getting It Right Every Time, Reliability and Its Importance. I want to warn you in this chapter, in case you've already read it, there's a lot of math and statistics in this chapter, and this is probably one of the toughest chapters in the book, but don't worry, we'll get through it. I'm not going to make statisticians out of you, but I think we can make sense of what they're trying to show us here whenever we're dealing with reliability, and that's one of the most important aspects of our test. So let's go ahead and start with the PowerPoint, and we'll get through this. Reliability. Reliability is a quality in our test that does the following. The question we got to ask, does the measuring tool you are using, like the test, measure something consistently? If you're trying to measure how well a student knows your content in your technical college class, is that test going to measure what it is you want those students to know consistently? And if it does, then we ought to see some kind of consistency among the scores that our students get, consistency among raters. You know, you can give your test in class, I could come back and give it, and we'd get consistent results. And also consistency across time. If you give this test over and over and over again, kind of like our test that the truck drivers give at our school, it's the same test. And so they could go back 10, 12 years, or maybe not that far, but let's say 3 or 4 years, and look at the scores that students got on every one of the tests that they give, and see if they gave fairly consistent results. So reliability is all about consistency. Now, how do we arrive at reliability? It's based on the different components of a test score. All right? You make 70 out of 100 on a test. Well, test scores will comprise the following. The observed score. That is the score you actually made on or get on the test. All right, let's say I made a 70 on a test. All right. All we got to do is just go out there and count how many right, how many wrong, and that's my observed score. But the true score is a little different. It's the accurate reflection of what you know. Maybe I misread a question. Maybe I just marked the wrong answer. Maybe I guessed right. There's a lot of different things that could happen to me to I guess challenge the validity of my observed score. But the true score, and that just may be a theoretical thing, would be if I took the test, and it would be an accurate reflection of what I know there on that test. And so the difference between the true score and an observed score is the error score. Now, are you and I going to go out there and do this for every test we give? Absolutely not. But you know, for testers, people whose livelihood is wrapped up in giving tests, like a lot of these standardized tests that you and I see given all the time, that's a major issue. You know, you want to keep that error as small as possible. So we'll go ahead and move on to the next slide here, which is sort of like a little mathematical representation of the observed score is equal to the true score plus the error. Now, your observed score can only be equal to this true score if we measure the trait without any error. This is also sort of a theoretical thing here. You know, there's nothing that you and I can put together that may not have some kind of error in it. You know, we just don't live in a perfect world. And so it's going to be pretty sure that our tests are not going to be perfect. But as this second bulleted point says, it's highly unlikely to measure anything without error. And so our observed scores will pretty much just be that. But your error is very important to understanding reliability. If your error increases, goes up, reliability goes down. That means you're not going to get the same results consistently. If your error decreases, your reliability will do the opposite. It will increase. And so we want to keep this error as small as it can possibly be from a testing standpoint. And we'll see some ways that we can do that as we go on. Now, what are some ways that we can get some errors in some tests? Well, trait error. These are sources of error that reside within the individual. There's nothing you and I can do about the individual. You and I can't take the test for them. And so they have to, you know, whatever they bring to the table that day, it's what they bring. You know, if they didn't study, they stayed out all night the night before, partied, they're not ready to take that test, well, chances are they're going to do poorly. And, you know, that score is not going to be an accurate reflection of what they know because they're worn out. Or let's say they're sick. They show up with the flu. There's no way that they can test accurately, feeling like they do. Method error are sources of error that reside in the testing situation. Maybe the instructions that you gave for the test are lousy. Maybe the environment of the room was bad. One of the things we try to do in our testing room where we give the compass entrance test is to try to get the room at a comfortable temperature very early in the morning, so that at least, you know, students that take the test can't say that it was too hot, too cold, and they were just worried about it freezing to death or burning up rather than taking the test. But that is a source of method error. Now, as we've seen, there is a impact that error can have on reliability. And here we see sort of a little mathematical expression of reliability. See, we got the true score right here, which would be the student's perfect score if they were able to take the test, and it would be perfect. But you see that here that you have true score plus error. Now, let's say the student made a 75 on the test. Well, notice how the true score plus the error is going to be 75, and let's say the error is 5. And notice that's going to equal 80. Now, what's important right here for you to know is that reliability is going to be a decimal number. It's going to be point something. So if 80 goes into 75 probably about 9 times. So that would be 0.9 something. But you see how it's a decimal value. So as the error component gets smaller, what happens to the reliability? Won't it go up? If this goes to 4, this goes to 2, aren't we getting closer to 75? If it was 0, if it was perfect, it would be getting higher, the higher 90s. If the error is bigger, then this number gets bigger and this number starts to drop big time. Now the question is, what would happen if there was no error at all? It was 0, it would equal 1. It would be perfect. But chances are you and I aren't going to see that. Now it says only random error impacts reliability. These are things you and I just cannot control. They're random. You know, students taking the test and all of a sudden electricity goes out. Do you and I have control over that? No, we don't. Or, you know, their fitness to be able to take a test. So we look at that as random error impacts. Now, what you'll see here is something called a reliability coefficient. That is a decimal. Reliability is calculated using a correlation coefficient. Correlation is an index of relationship. That's what a correlation. What type of relationship is there? How much do two variables have in common? Now, your reliability coefficient will be a decimal between 0 and 1. And the higher the number, the more reliable your scores are from that test. That's all you need to know. If it's in the 9s, maybe the high 8s, 0.8s, 0.9, got a pretty reliable test. If it's below that, in the 7s, 6s, 5s, not so reliable. That's all you need to know. Now, we're going to answer some questions right here about the types of reliability. When are they used? How are they used? And what do they mean? And you will find this table 3.1 in your textbook. Different types of reliability. You've got test-retest reliability, parallel forms reliability, internal consistency reliability, and inter-rater reliability. Now, what do those things do? All right. Test retest reliability is where you give the same test two different times, or more than two different times. And then you start seeing if the scores are consistent. And the big thing here is over time. You've got to keep giving this thing over and over again. I guess the best example would be the compass test. We give that thing probably thousands of times every week. And since it's an internet version, you're taking the same scores from a database all over the United States. And so that kind of test over a period of time can be measured to see just how reliable it is. Whether you take it in Alaska or take it in Louisiana, your results ought to be reliable, that you can count on the results as being true. Now, parallel forms is a little different. You take one form of the test, and then you take the same test of the same context, but not the exact same test. For example, let's say you got a 100-question test. All right? You take all the even-numbered items and make a test out of that and give it to some students. Then you keep all your odd-number test results. And later on, give that test to some students and see what their results are. And then you can kind of measure whether or not the tests are reliable like that. You know, I guess that's sort of an example with the compass, because it pulls random questions from a database. And so if a student wants to retest, there's no guarantee that they are going to get the same questions like you and I might do with a test that you and I make. They're going to get a different set of questions, and then we're going to see if they know what they know. And I've seen that before, where a student says, well, my scores went down. Well, maybe they had a good day testing that day, or else they guessed right. Because, or then maybe also they got some harder questions. Or maybe some math or English or reading. So parallel forms is another way to be able to get reliability. Internal consistency reliability. You do that whenever you want to know if the items on a test assess one and only one dimension. You know, you don't want to do all kind of things with every question on a test. You want it to, focus in on what you want the students to know. And so you correlate each individual item score with the total score. This is a whole lot of work right here, but you have to go back and look at every single question on the test and then correlate it with the total score that a student made on a test. Something that you and I don't have to worry about doing. And then inter-rater reliability. If I'm going to give a test, or you're going to give a test, and we're asked to rate some things, am I going to give a student a higher score based on that criteria, or somebody's going to give a lower score? I guess it's kind of like these TV shows with this that these students, these people sing. I think it's American Idol, something like that. They got some judges on there. I don't know if it's what they need to do to kind of make the show interesting or whatever, but every one of them's got a different opinion about what they hear, what they see. And you want to be consistent. whenever we rate things. And I don't know if they have a scorecard in front of them or what, but that's the type of thing that you're having to deal with. You know, their scores ought to be fairly consistent if what they're measuring is reliable. To kind of look a little bit more at test-retest reliability, it's a measure of stability. Is a test reliable over time? You know, years and years, months and months, between the times that we test, between measurement of time 1, time 2, time 3, whatever it is. And then you kind of divide your scores together, get a correlation of the two scores, and that's an estimate of reliability. Your problems. A student takes that test enough times, the chances are they're going to probably get some answers right that they got wrong. And then time and testing interaction. You know, you take a test one time, you go back and have a chance to study. Well, that kind of offsets the first time you took it. So it does have some drawbacks. Parallel forms. It's a measure of equivalence. Are the tests about equal? Now, the problem is we've got two different forms of the same test. That will they measure the same thing? So we've got two different forms, two separate test occasions, and then the correlation between the two forms provides a reliability estimate. Now, main problem, it's difficult to create two forms of the same test, and two equal ones. And then fatigue. I mean, you're going to test people to death. You know, chances are the more they get tested, the worse they're going to do over time. Internal consistency. And remember, that's about taking every item of the test and measuring it against the total score. Well, that kind of gives you the opportunity to look at each item. Are they consistent with each other? Do these items represent only one construct? Are they focused on only one thing and one thing only? There's some ways to look at internal consistency. These two guys right here are no fun. They're major statistical computations. Split half, very simple thing. All you do is put together a test, split it in half, and give the test to one group and give the other test to another group, and then compare the results. This one's used quite a bit in educational research. The split half, but then the Cronbach's alpha and the KR20, you get into some serious mathematical computations there, and you're going to see some examples of them here in just a minute. All right, split half, you split your test and compare your two scores. You do the odd numbers make one test, even numbers make the other test. Don't split them in the first half and the second half. You may have two different types of test questions or anything or something like that. And more often than not, we usually, whenever we start doing tests, we start from the front of the chapter to the back of the chapter. All you do is, even odd is usually the best thing to do. You correlate your splits using a Spearman-Brown statistical analysis. Major problem with that, you split this thing different ways, you get different estimates. Again, it's not perfect, but nothing is. And here you see your Cronbach's alpha, and this is the symbol for the Cronbach, little alpha symbol right there. This thing will compute all your possible split halves. And then they usually use this for personality testing, where there's no right or wrong answer. You're just putting in what applies to you. Normally, you and I don't give a whole lot of tests like that, but that's the formula right there for a Cronbach alpha. And if that wasn't bad enough, look at your Cooter-Richardson 20. Computationally, it's about the same as the Cronbach alpha, but this is better to use where there is a correct or incorrect response. Remember, Cronbach, there's no right or wrong answer. This one is. Now, big assumption. It assumes that the true score and the error score on all the items are identical. Now, that's a big leap of faith, but that's what you got to do in order to run your Cooter-Richardson. Iterator reliability, again, that's if two people come up with maybe two different measures, but it's a measure of the degree of agreement. Do they agree on the ratings of performance or behavior? You can take a percent of agreement among the raters. You take the number of agreements divided by the number of disagreements, and that will give you a correlation there of the rater scores. Because let's face it, there may be some things we would agree on. There may be some items that we may have some problems with, and this, you just divide one into the other, and that gives you a correlation there. Now, to interpret reliability coefficients, remember it's a decimal. For a test, retest, it's between 6 and 1, pretty good. In a rater, agreements ought to be about 85% or 0.80 and above. Internal consistency, you ought to have a 0.7 or higher. But high reliability doesn't mean high quality. A test can be reliable and not valid. Now, what does that mean? Well, you can get the right answers consistently, but yet you can also get the wrong answers consistently. Reliability is about getting the same results. And if your test questions are bad, they're going to yield bad results consistently. And that's not a valid construct. We'll talk about validity later on. Some ways that we can increase reliability. Increase the number of items on the test, within reason. The more test items we have, the more we have to know, get a good feel for what the student knows. Then eliminate your bad items. Got some bad questions, get rid of them, change the questions. Standardize your conditions or the instructions. Make them simple. Get your environment conducive for testing. Moderate the degrees of difficulty. Do you have hard questions, easy questions, medium difficulty questions? Try to get a good mix of those right there. Minimize the effects of internal events, like fire alarm going off in the middle of testing, or things like that. And then maintain consistent scoring procedures. I would say that grading a test in the middle of Monday Night Football or a Saints game would probably be something that I wouldn't want to do, because chances are, depending upon the score, my grading may be a little bit more lenient or difficult or tighter, depending upon my mood, especially maybe on like essay questions or something like that, or fill in the blank. So uh, you know, you use some common sense here.